So in class, we've been talking about solving free fall problems, and we realized that finding out the time it takes for an object to fall a certain displacement gives us a quadratic equation. And there are times when we might know the acceleration and we might know the starting velocity and we know how far it falls, but we don't know the time. And so we have something like what you might have seen in math in 7th or 8th grade, and we need to figure out how to solve it. So I rearranged the equations into the form that we would actually use to solve it. So for physics, it would be 0 equals 1/2 times the acceleration. So that's often going to be 5 t squared plus the starting velocity times t minus the displacement. I've subtracted it over to the right-hand side. So the whole thing equals to 0. The math people will write this with coefficients a, b, and c, where a, b, and c are just random numbers. Here, a is not acceleration, just something. Okay, and I'm going to show you how to solve this the math way, and then we'll talk about the units at the end. Okay, so if you have a quadratic equation, the first thing you should do is make the coefficient of t squared a 1 by dividing the whole thing by a. After you've done that, you would try to factor it, but if it doesn't work factoring, if you can't write in the form t plus something times t minus plus or minus something else, then you might have to go ahead and complete the square. But if that doesn't work, then you may need to complete the square. The idea behind completing the square is to be able to take the square root of something with a t in it, so you don't end up with a plain t and a square root of t. And to figure out how to do this, we're going to focus on the terms with the t to complete the square, and we're going to ignore this c over a, which would just be a number. So I'm going to write this with that c over a thing out of the way so I don't have to deal with it anymore. So I'm going to subtract it off to the left and really focus on the remaining piece. So as it turns out, to complete the square of the things on the right-hand side, we need to add a number that is equal to half of the first order term coefficient squared. So half of this squared. But we can't just add that coefficient to the right-hand side without also adding it to the left-hand side. So I have to do the same thing over here. I've added the same term to both sides of our equation. And now that I have done my due diligence, I can write this right-hand side as a square. So it's t plus b over 2a. All squared. So I'm at the point here where I can take the square root of both sides and then finally solve for t. But before I do that, I'm going to clean up the mess that is the number on the left-hand side a little bit. Now for this, you can just close your eyes till it's over. You'll see what I did later. Okay, so my rearranging on the left-hand side is done. If you want, pause and look and see what I did. Now I'm going to take the square root of both sides, square root the left side, square root the right side. Okay, so when we take the square root of a square, the answer is plus or minus the thing we took the square root of. And the square root of this thing on this other side is just this big mess. Okay, I'm going to write all the numbers back in red. So finally, I can solve for t. I'm going to have two answers. One when the right-hand side is positive, one when the right-hand side is negative. So here's the right-hand side positive answer. That would be t equals square root of b squared, all this stuff over 2a minus, I'm going to put the numbers in. And now when we have the negative solution, so that would be minus t equals this whole thing on this side, minus t plus, okay, b over 2a. To get that t truly isolated, we're going to multiply through by -1. When we do that, the t flips to positive. This thing becomes negative, and the b also becomes, well, let me erase it, also becomes negative. So for those of you in the know, we have just indeed derived the quadratic formula. The quadratic formula is the general expression for what happens when you complete the square. And somebody's done all the math for you, so you could just plug your numbers in and solve. So I promised I'd check out the units for us. So let's remember what our units were. This math A is 1/2 of our acceleration. So this A thing has units of meters per second squared. B for us was our starting velocity, so that has units of meters per second. And C for us was a displacement, so it should have units of meters. Okay, so let's go through and check the units of these terms. We've got a b squared minus 4ac square rooted, all divided by 2a. So as far as units go, b is meters per second, all squared, minus 4 doesn't have any units, but a does. It's meters per second squared, and c is meters over 1, and then divided by something not in the square root, 2, which has no units, and meters per second squared. Okay, so it looks like both terms in the numerator have meters squared over second squared. Like if I distribute out this exponent and multiply these 2 meters together, so when I take the square root, the numerator is meters per second, and then it's all divided by meters per second squared. So these meters up here cancel, one of these seconds cancels, so this is the same thing as 1 divided by 1 over seconds, which means that your seconds flips up into the numerator, and that is indeed a time. So this whole term has units of seconds, which is good, yay. The second term is b divided by 2a. So let's see what's going on with that. We've got a meters per second divided by meters. Oh, shoot, meters per second squared. Oh, look, so this is the same thing. This ends up being 1 over seconds. So the unit is seconds. Okay, so this also has units of seconds, which means when we plug the numbers in, it all ends up with units of seconds. And because these two terms have seconds, this one will also have seconds, and this one will also have seconds, and everything works, and our units work, and we're so happy. So I'm going to do one last slide for the problem that we started in class. I'm going to do it numerically, and I'm going to try to be really smooth. So we've got this ball that we've thrown down at t equals 0 from a starting position of x equals 0 with an initial speed of 20 meters per second. So again, we've chosen our coordinate system to have the origin where this ball is, and we've picked down as positive, so this is our positive direction. And we are interested in knowing, really we want to know how fast this ball is going when the position is 100 meters below where it started. So for us, that's positive 100 meters. We don't know the speed of the ball here. We don't know how long it's taken to fall. We do know that while it's falling, it has free fall acceleration of down. Okay, so the acceleration is going to be Galileo's constant, which I'm going to use 10 meters per second squared, and I picked down as positive. So this thing is going to be positive. Okay, so this is the question we're trying to solve. Working with the equations we have, I don't know how to find the final speed without finding a time. And the only way I know to find a time is to use the displacement equation. So that being the case, I have to deal with this first. Okay, so plugging in numbers, I've got 100 meters equals 1/2 times the gravitational acceleration, which is 5 meters per second squared times t squared, plus 20 meters per second times t. Okay, so this is a gross yucky polynomial, I can already tell. So the first thing I want to do is get the t squared term by itself. So I have to divide everything by 5 meters per second squared. Okay, so 100 divided by 5 meters per second squared is 20 seconds squared. 5 meters per second squared divided by 5 meters per second squared just gives me 1 t squared. 20 meters per second divided by 5 meters per second squared is 4 seconds times t. So this thing is a unit. Okay, 4 seconds times t. And then I'm going to just do this by completing the square. So to complete the square here, I need to take this and divide it by 2. So that would be 2 seconds, and then square that 2 seconds. So I would add 4 seconds squared to both sides, 4 seconds squared. Okay, so whatever I do to one side, I do to the other. And then suddenly I actually have a square here. So it is t plus 2 seconds, all squared. We can double check that this works. Let's check. Let's go check below. I'm going to write it at the very bottom here. Okay, so t plus 2 seconds times t plus 2 seconds gives me t squared plus 2 seconds times t, that's the second term here, plus 2 seconds times t, plus 4 seconds squared. Okay, and these units work out. I've got a t squared plus 2 seconds t plus 4 seconds squared. Okay, so that's all fine. And then on the left-hand side, I've got 24 seconds squared, and I want to square root both sides. So now I have the square root of 24 units of seconds equals t, and plus or minus, plus 2 seconds. So I have two solutions. The positive solution would be, and when I say positive solution here, I mean the solution with this positive. It's that. It's not that t will be positive. That's just the positive one. So t will equal the square root of 24 seconds minus 2 seconds. And then the negative one, I'll write that one over here. That's this one. Would be the square root. Okay, so it would be the square root of 24 seconds plus 2 seconds. But then I want to multiply everything through by negatives. So the 24 would be negative, and this positive sign would become negative, and that would be equal to t. So the answer, the answer that ends up being positive is this one. So the time it takes this object to fall is the square root of 24. I don't have my calculator here, but this is a number. You just take the square root of 24 in your calculator, and then you subtract 2 from it, and that's the time. I found my calculator, and the time it takes for the ball to fall 100 meters is 2.90 seconds. And to find the speed when it's fallen that far, I would take this time and I would plug it back into our other equation, v equals at plus v naught. So again, we're using positive 10 right now for the acceleration times 2.9 seconds plus the starting velocity of 20 meters per second. So these are both going to be speeds. So I have 29 meters per second plus 20, so that ends up being 49 meters per second in the positive direction, which for us is down. So when it's fallen 100 meters, the ball is moving 49 meters per second in the downward direction.